All right, sorry, I realized my mistake. In the last video, I wasn't differentiating properly. Yeah, we are back to question 3, and we are finding acceleration as a function of time. We've already found velocity as a function of time, and we're going to use that and we're going to differentiate. And this is chain rule. Chain rule. So we can rewrite this velocity as negative 16. Sorry. As negative 16 is 8t plus 1 squared. And with chain rule, sorry, that's negative 2 squared. We're going to take that 2 down to be multiplied. We're going to take everything in the brackets and then reduce this by 1 and multiply by the derivative of what's in the brackets. So this is going to give us an answer of A is equal to 256 over 8t plus 1 cubed. And there is our answer there. Sorry for the confusion in the previous video. Yeah, I had to cut it off because I wasn't too sure, and I forgot that I need to use chain rule. I may or may not have Googled it. That is okay, because we are making these mistakes now and not on the exam. Okay, now we're on to problem 4, and it's a very similar question, except we have an initial velocity, so we have a particle moving along a straight line with initial velocity, and we're given acceleration as a function of v, and we want to determine how far it travels before it stops. So this is our clue here, determine how far it travels. So that means we need a function of x. So we are going to be using the equation. Oh, sorry, we're also going to need to know how much time it takes. So we need it as a function of t. Okay, to start with this equation, we want to find our acceleration with respect to x. Right, we need it as a function of x. So there's this equation that we are given in our sheet, which is a equals v dx over dt. And that is what we are going to use to solve this first equation, this first part of our problem, because we are given dx and our dt, as well as our v. And from this equation, we can get the form a dx equals v dv. Okay, so using this form, we are going to solve for our first part of our problem, which is determine how far it travels before it stops. So, same thing, we're going to take, this is negative 1.5 e to the half, and this is with respect to dx, and we have velocity with dv, and let's get this dx on its own. So let's isolate our x. So in order to isolate for x, we are going to need to integrate. So, let's get this x on its own. So we have dx equals v dv, and it's divided by our acceleration. And when we integrate both of these sides, we are going to get x is equal to, and in our integral we have two bounds. We know that our initial velocity is 6, so that is going to be our bottom bound, and we want to determine how far it travels before it stops. So that means that when it stops, velocity is going to be 0, so that is going to be our top bound. So this is like saying So we're going to move that up. Negative 1 over 2. So this is going to give us negative. So we're going to kick out this 1.15, sorry, 1.5. So this is also equal to, rewrite it, negative 2 over 3. That's just 1 over 1.5. Integrated in this. This is going to be v to the positive 1 over half, dv. And then we get 3 over 2, v to the 2, sorry, 3 over 2, so it would be 2 over 3. 0, 6 to 0. Okay. So now when we integrate, that is going to give us negative 2, 3, and for our value of v, it's going to be, starting at the top, and that's minus 2 over 3, and this is 6 to the 3 over 2. And it's going to give us x is, that's just going to be 0. So this is negative 2 over 3 times minus 2 over 3, and then 6 to the power of 2, 3 is 12. So that's times negative 4 divided by 6. And that's going to give us x is equal to 6.53 meters. Okay, that's our first part done. So remember we used the form a dx equals v dv because we had v and we need to find x. So now I want to determine how much time it takes. So now we need something with time in it. So a is equal to dv for dt. And this is great because this has our v and this has our t. Right, we're looking for t and we're already given v. So we're going to write this as dv over dt instead of our a on the left side. And on the right side, we are going to put our existing equation. Okay, and same thing, we're going to move all the v's to be together. So we're going to get dt on its own. We're going to get 1 over negative 1.5 v to the half dv. Okay, and we're going to integrate to get time on its own. Oh, and again, we are integrating from a velocity of 6 to 0. It's going to give us t is equal to, we're going to kick this out again, so it's negative 2 over 3. And this is going to give us 2 v half and 0 6. And this gives us t is equal to just negative 2 over 3. And this is going to give us negative 2 root 6, which is equal to 3.27 seconds as our final answer for our second part. All right, so that is part 4. Again, we had to use different forms to transform our variables. So we used a dx equals v dv for our first one to determine how far it travels before it stops, and we used the bounds of 6 meters per second as our initial and 0 meters per second as our final. And for part B, we used a equals dv over dt We already have dv in our function, and we wanted to transform it to dt. Okay. So, problem 5. On its takeoff roll, an airplane starts from rest and accelerates according to this function here, where our a0 is constant, because that is the thrust from the engine, and this second term here is caused by aerodynamic drag, and you notice it's negative, so it's decelerating, which makes sense because the plane is working against drag. So we're given our value of our k, and we want to determine the length of the runway that's required for a takeoff speed of 250 kilometers an hour. First things first, before anything, I'm going to transform this into meters per second. So that's going to be 250 kilometers an hour. Let's get rid of the kilometers. 1,000 meters in a kilometer. Let's get rid of our hours. In 1 hour, we have 3,600 seconds, and that is going to give us EF is equal to 69.4, I believe. 250 times 1,000, then divided by 3,600. Oops. Yeah, 69.4 meters per second. And that's going to be our final speed, because that's the speed that we want to reach. So collecting our other terms, we have V0 is equal to 0 meters per second, because we're assuming that a plane starts from rest before it starts taking off. Yeah, so we're going to start with that. So we need to make a in terms of x. So we need our acceleration in terms of because right now it's in terms of v, so we want to get that x back in there. So we can use that form from our previous question, a dx equals v dv, because we are given our velocity. Sorry, our velocity exists as the variable in our acceleration, and we are looking to transform into x. So we are going to use this. So let's start. This is our a dx equals v dv, and we want to do it with that term excluded, with our drag term. So that means I'm going to scribble that out. So in that case, we are going to have, let's move that over, so this is dx equals v dv, and we're going to divide by our acceleration, which is just a0. Okay, and once we integrate, we know that we are integrating from our initial speed, which is 0 meters per second, to 69.4 meters per second, which is 250 kilometers an hour. We're going to get x on its own. So this is going to be, a is a constant, so we're going to kick that out, and our constant was 2. And this is going to be 69.4 on our top. It's going to be x is equal to half. This is half v squared, 69.4 and 0. And this is going to give us 69.4 squared divided by 2, divided by 2 again, and this is going to give us 1,204.09 meters, with the drag term excluded, which is the answer to our first part. So then for our second part, we want to include that drag term, which means we are going to be using our full equation. So this is a equals a0 minus kv squared. And we are going to use the same kind of function, because we still want to find length. So we're going to use a dx equals v dv. All right, and from this we have, we're going to move our a over to the other side. This is v, and our a was equal to a naught minus kv squared dv. Again, we are going to integrate from our bounds. Right, and this integration is a little harder. So it's going to give us negative 1 over 2k, right, because that's what happens when we derive this part here. And that is going to give us ln of ln of a naught minus kv squared. Yeah, so I'll go through that integration just so you can see. Right, because it's going to give us, because if we were to just kick out that dk, that means that we can account for this v at the top, and that is why we get ln a naught minus kv squared times negative 1 over 2k. And this was from, all of this is from 69.4, sorry, 0 to 69.4. Okay, and all that's left to do is plug in our values. So our value is negative 1 over 2, 0.00004. Times our ln, and this is 2 minus 0.00004, 69.4 squared. Okay, so 2 minus 0.00004 times 69.4 times 69.4, this is our ln, and this is times 1 divided by 2, and this gives us our value of x, which is equal to 1,269.45 meters, and that is with the drag coefficient. Okay, so those are all of the questions from the assignment. So the biggest thing, make sure you're looking for if you can use constant acceleration or not, and think about which terms that you already have and which terms you want to transform into for your variables. So look at what the question is asking and figure out which form you have to transform into. Yeah, thank you for watching. I hope you found this video helpful, and yeah, let me know if I made any mistakes in my work, because there was a couple from the last one. But yeah, thanks for watching.